Okay, let's start to put together all our energetics, kinetics, and equilibrium information and start to apply delta G to our equilibrium situations. The last little bit of this video will talk about rate law, which is higher level kinetics, which we're about to start. So it's worth just putting these notes to one side, maybe coming back and looking at this video again after we've done higher level rates as well. So let's get started. So in energetics, we've assumed that the reactions all go to completion and all reactors are converted to products. We talked about this when we were introduced to equilibrium as well. And we know that equilibrium reactions don't go to completion. They will reach a steady state where the concentration of reactants and products remains constant, the equilibrium state, as long as the system is closed. So in this, the rate of the forward reaction equals the rate of the reverse reaction, even though the concentrations may not be equal. Don't forget that. So when we talk about Gibbs free energy in equilibrium, we talked about the fact that change in Gibbs free energy is the work that is available from a system. Okay, so in equilibrium, the system is not able to do any work because it is in that constant forward and reverse at equal rate. So at equilibrium, delta G can be considered 0. So we have these three conditions for delta G, that being if delta G is negative, the reaction will proceed in the forward direction. It will be spontaneous. If delta G is positive, then the reaction proceeds in the backward direction. And then delta G equals 0, the reaction is at equilibrium. Okay, so this gives us a relationship to delta G when we talk about equilibrium position and shifts in equilibrium. So as delta G becomes more negative, the reaction favors the products. So delta G for the reaction will be below 30 kilojoules per mole. The reaction can be considered complete. Okay, so it goes completely to the right in that case. So when we talk about the free energy change, or delta G naught, we calculate this using delta G naught of the products minus delta G naught of the reactants in the same way we have for enthalpy and for entropy so far, using the table 12 data. Remember, this is table 12 from our data booklet, which was thermodynamic data at standard states. Okay, under standard conditions. So at equilibrium, delta G naught of the products must equal delta G naught of the reactants, because this equation here is going to equal 0 at equilibrium. So if we look at this in terms of reaction progress and looking at an energy profile diagram, as we start at the reactant side, the total free energy of the reactants and the products, that energy is going to decrease. Okay, spontaneous reaction, delta G is negative, so we're going to head in this direction until it reaches a minimum energy point. That minimum energy point is going to be the equilibrium mixture. In this case, we can see that this sits towards the product side of the reaction progress. So if this is delta G naught of the reactants and delta G naught of the products, delta G will be negative, spontaneous reaction heading to this point here, which is equilibrium, which will be the minimum amount of free energy in the equilibrium mixture. So in this reaction, we can see that we have this minimum point reaching where we're close to pure products. However, in this example here, we have delta G products and delta G reactants. In this case, we have a positive delta G, and the minimum point of this curve is sitting with the equilibrium mixture closer to the reactants. So the spontaneous reaction here is moving towards this minimum amount of energy, which favors the reactants in this case. So as the reaction progresses, work is done by the system, so the total free energy decreases because we're using up that free energy. So it decreases both for the products and the reactants. So there is a minimum point of free energy where they're both at their lowest, and this is equilibrium. The decrease in free energy during the reaction, so the decrease in its ability to do work during the reaction, appears as work done by the system or as an increase in entropy. So as delta G decreases, then entropy should increase. So when the system has a minimum amount of free energy, the entropy is at a peak. So delta G is going down, and as it does, delta S should increase. Okay, so this maximum entropy, minimum free energy, occurs at equilibrium. So if we summarize these and use delta G to predict spontaneity in the position of equilibrium, when delta G is greater than 30 kilojoules per mole, we have a spontaneous change being impossible. There's no reaction. The products and the reactants are much less than 1. If it's 0 kilojoules per mole, okay, is less than the delta G of the reaction. So if it's between 0 and positive 30, the partial reaction producing the equilibrium mixture will occur. Delta G of the reaction being 0 kilojoules per mole, this will produce the equilibrium reaction where it's equal to 1. 0, so if we have it being less than 0, so delta G is negative in this case, then we're going to have the products over the reactants being greater than 1, so we will have more products, whereas this one we had more reactants. And then delta G being less than 30 kilojoules per mole, we're going to say that we have a complete reaction. The products over the reactants is much greater than 1, so this is favoring the right-hand side, so it's going to completion, whereas this one basically is saying that we get mostly reactants. So when delta G is large and negative, the reaction is spontaneous and the mixture is mostly products. That's what we're getting from this. When delta G is large and positive, it's non-spontaneous reaction and the equilibrium mixture will mostly be reactants. So looking at these again, this is another these curves that we looked at before. What you'll have is our y-axis is delta G. So in this case, we've got the Gibbs free energy of the reactants because we have reactants over on the left-hand side. On the product side, we have G of the reactants. So going from products, reactants to products, we have a decrease. So we have a delta G for the reaction coming down, so it's going to be negative, giving us the equilibrium position at the minimum of this graph being products. And then when we have the large positive delta G, we have the equilibrium mixture favoring the reactants. Okay, so this is going to give us a new equation. This equation is another one where we just need to be able to find the values to substitute them in, and the equation is given in table 1 of your data booklet. This equation gives us the link between Kc, the equilibrium constant, and delta G. Okay, because these both relate to the position of equilibrium, we can write this equation here, which relates the two terms delta G and this K, which is Kc. The equation is given as negative R, where R is the gas constant, also given in your data booklet, T, which must be given in Kelvin, okay, and then lnk is the natural log of the equilibrium constant. Okay, from this we just substitute in the values relevant to the situation. When we use this, okay, so this is going to be the temperature of the equilibrium. Remember that Kc is constant only for a set temperature, and you're going to have the Kc value. R is a constant given in the data booklet. We can calculate delta G. delta G, sorry. If Gibbs free energy is negative and the LNK is positive, we have mainly products. If delta G is positive and LNK is negative, we have mainly reactants. If both are 0, then we have appreciable amounts of both reactants and products in the mixture. So different reactions will have such different equilibrium constant values due to the different free energy values. Delta G is dependent on delta H and delta S for the reaction. So the equilibrium constant for a reaction is determined by the sign and value of its free energy change delta G and through this equation. And remembering that delta G is also dependent on delta H and delta S, these in turn have an influence on the equilibrium of a system. Last note in this is going to be on kinetics. What I might actually do is do a second video for this where we talk about kinetics, and we can add that in once we've done the higher level kinetics. So looking at this, the key thing here is that we can have this equation, which is given in data book in section 1, and this relates the equilibrium constant Kc with delta G. So you need to know this equation and then be able to know these situations where we have a negative delta G and LNK being positive gives us mostly products. Positive delta G, LNK being negative, we get mainly reactants. Okay, and remembering that a negative delta G indicates a spontaneous reaction. So in this case, it kind of makes sense that if we have a positive delta G, the reaction isn't going to proceed far in the forward direction. So it's worth keeping that in mind to try and get these straight. We'll do some practice calculations on these and hopefully it will start to coalesce and start to make sense. But as I said, most of the questions on these will just require you to know the equation and be able to substitute in the values to be able to solve delta G, and know that delta G when negative means that the reaction will be spontaneous. And if we have Kc, LNK being positive, we have mainly products. I will see you in class.